Hello, everyone. My name is Gregory Kuros, and today I'll be talking about associative memory and how it can be used in conjunction with quantum annealing for pattern recognition. This work was done with some collaborators at Oak Ridge National Laboratory, and it is part of a DOE Office of Science grant. Now, we're focused here on pattern recognition, but really from the perspective of high-energy physics particle detection. Now, this is actually quite a difficult problem to solve in this domain, and it is because of the fact that the pattern matching accuracy is highly dependent on the noise, the detector resolution, as well as the number of simultaneous particle tracks that we have. Now, combined with the fact that these pattern libraries may be very large, and also that these patterns themselves may be quite large, makes this a very challenging problem. Now, we look to quantum annealing as a potential way of circumventing a lot of the issues with typical pattern matching or classical pattern matching for a couple of different reasons. One, we look for it to enable more accurate pattern matching, and essentially this is due to some theoretical results which suggest that that the learning capacity, or essentially the number of memories that can be encoded into the model and while still maintaining high accuracy, can be greater in the quantum case than in the classical case, at least in theory. Now, what this means is that we wouldn't necessarily see a quantum advantage from the point of view of runtime, but rather from the point of view of memory capacity, which sort of is a new way of kind of thinking about quantum advantage. Furthermore, from sort of a more traditional quantum annealing perspective, we see that because of the sampling properties of quantum annealing, that we obtain a set of low-lying energy solutions, and having multiple candidate tracks, or essentially multiple candidate patterns that match a particular pattern that we are trying to match, that could be very useful for track recognition. Now, pattern matching itself fits within sort of what we get from the detector and the eventual track reconstruction. Our detector itself will give us a series of detection events, and it is a pattern matching algorithm's job to distinguish between signal and background. And once it's done this, it takes those signal patterns and sends them off essentially to the track recognition algorithm where the tracks can be fit. In this case, or in this sense, I should say, the pattern matching algorithm acts to sort of reduce some of the computational complexity that the track reconstruction algorithm will face. Now, as I mentioned, we're focused here on associative memory and how it can be used for this particular problem. Now, this still boils down to sort of the same problem of sort of supervised learning. And so here, our training set now is going to be a set of memories that we're encoding into our model. And each one of these memories is going to be given by a key or a label and a value, which represents, the value represents the actual pattern that we're trying to encode. And so we take this training set and we encode it into, or essentially learn it into our associative memory model. And then we give candidate or probe patterns to our model to classify. And what this does is it not only tells us whether or not, let's say, the pattern is a background or signal, but it can also actually tell us which particular pattern that is encoded into the model the probe is most closely related to. So the probe itself may be a pattern that is directly encoded into the model, or it may be some imperfect or partial a version of what's encoded into the model. So it actually gives a fair amount of information. Now, there are different ways of choosing how one builds the model, and how one builds the memory itself. Now, we consider two here. One is sort of the traditional associative memory model and the content addressable memory model. Now, in the case of the associative memory, the sort of traditional approach, the difference can be seen here from sort of a neural network perspective. So if we look at the AMM version here, we see that we allow for interactions between keys and interactions between values, which is distinct from the content addressable memory part. while in both cases we see a bipartite structure between keys and values, we see that whether or not we allow for those interactions between keys and values, or say self-interactions between them, is actually going to change a bit the model, and we'll see how this actually affects the overall quantum annealing problem that we're eventually trying to solve. But all of this is just to say that there are different ways in which we can encode the problem, and different ways in which we can sort of distinguish keys and values from each other. Now, given now that we have an associative memory problem, how do we encode this into something that a quantum annealer can solve, essentially an optimization problem, or finding the ground state of an Ising model? Well, the first thing that we do is we take our set of patterns or memories, and we encode them using a learning rule. And that will allow us to achieve a matrix W, in which that will make up actually the strength of interactions between our qubits. Furthermore, we will take our probe memory and use that probe to set the local biases of the qubits as well. Now, theta here is sort of like a global bias term that can control essentially the probe strengths. Now, if we take theta to be equal to 0, everything is dominated by the interaction Hamiltonian. And so what this actually does for us is it tells us that the ground state manifold will be degenerate, and it will be set such that the ground states will correspond to the patterns that we are trying to, or that we've encoded into our model. And what this bias term does when theta becomes non-zero is it starts to actually bias the ground states and essentially separate out those states which most correspond to the probe memories that we're trying to match to. So from this perspective, we see that this sort of traditional associative memory problem can be related to essentially the finding the ground state in this quantum annealing perspective as a problem of essentially separating out ground states and determining those ground states, or essentially hitting those ground states with the quantum annealing. So now, now that we have this sort of representation that allows us to perform quantum annealing, we can sort of distinguish between the associative memory models and the content addressable memory models. And so this can be seen by looking at this weight matrix W. So imagine that you have a set of memories where now each one of these memories we distinguish with keys and value pairs, and we use our learning rule to obtain this weight matrix W. And the weight matrix W, because of our bipartite structure, we can break it out into a block structure where along the diagonal we have the key and value interactions, and then the remaining terms correspond to interactions between keys and values. The main difference from this perspective between the AMM and the QAMM approach in the quantum case is that we essentially zero out the diagonal terms in the QCAM case. And already you can see that how this affects the overall, you would expect to affect the overall performance of a quantum annealer, in the sense that now we have lower demands already on the qubit connectivity. And we'll see how that affects the overall performance later. Now, thus far, I've sort of alluded to this learning rule, but I haven't really said what our learning rule really is in this case. Now, that is actually determined by the data set that we actually choose. And we focus on a toy model here. And we do that because we really want to understand the performance of the algorithms as a function of different parameters, or different characteristics of the detector. So namely, the detector noise, efficiency, or the detector size. And so what we do is we focus on a system where we have 3 layers, linear layers of our detector. And we vary the detector segment size. Basically, we can increase or decrease the size of the detector cell. And we can also control the efficiency of each detector cell itself. And so when we do this and we look at sort of the background and signal patterns that we obtain from our simulations, we find that there's actually a fair amount of overlap between signals and backgrounds. And so what this means basically is that this creates quite a difficult problem for the associative memory recall. Actually, the more orthogonal the memories are, the better performance we expect to see. However, we can deal with this by choosing an appropriate learning rule. Namely, if we choose projection learning rules, these are known and actually designed to sort of disentangle memories and essentially remove some of the interference. And so we use that here to enhance the performance of our associative memory models. Now, in addition, we also have a choice in our classifier that we choose. Because we're doing adiabatic quantum optimization, we can either choose energy or we can choose classification bits in order to classify our information. And so here I'm showing a couple of different scenarios that we consider here. We focus on here a 24-bit detector, which means essentially 3 rows of 8 cells, and only on the case of where we have 4 signal patterns encoded, and we will change this here in a bit. Now, we can vary sort of whether or not we encode signals only in the model or signals and background. And depending on how we do this, we'll see different effects on the overall performance and the classification, the classifier that we choose. So I'd like to call particular attention to these cases here and show that essentially when we have signals only, that the classification based on classification bit here, average classification bit, is that we see that we're not able to really perform classification very well. And this is really due to the fact that we've only encoded signals. And so this can be seen here because each one of these subplots, we have this diagonal line, and this diagonal line separates background patterns from signal patterns. Now, the recall that I'm showing here is I've encoded a certain number of signal patterns, and my probe memory is either a signal pattern that is encoded into the model or a background pattern that either is or isn't encoded depending on the type of scenario that I consider. In this case, there are no background patterns, and we see that it is unable to determine what or classify correctly a background pattern. However, from an energy perspective, we see a distinction between the energy of background probes when we use background probes as opposed to using signal probes. Contrastly, we see that in the case where we encode both signals and background, that we're able to obtain better distinction in the classification bit. However, in energy, as essentially expected, we see that the energy is fairly degenerate because of course we've encoded both signals and background into our model. And so what this says is that basically depending on how we decide to encode our information or what information we decide to encode into the model, that will actually dictate which type of classifier we choose. Now, as we start to increase the number of signal patterns, that are essentially the pattern density, we see that the classification bit, we see that it's harder to classify. Whereas in the energy case, we see that well, while it does appear to get worse, it isn't actually bad enough such that we can't distinguish between signal and background. And so let's look at this sort of more of a global perspective and see how this changes as a function of detector size as well as pattern density. So we do this again by looking at patterns that are encoded, signal patterns that are encoded into the model, or background patterns that are either encoded in the class bit case or not encoded in the energy case. And we do this by using receiver operator condition curves, or ROC curves. Now, each one of these subplots here shows the true positive detection rate versus the false positive detection rate. And the idealized scenario is to be up in this left-hand corner up here. And along this dotted line is essentially what we're trying to avoid. Now, each one of these subplots shows a certain number of detector cells here, and the difference between each one of these rows, or I should say, each one of these columns that I will show, will be the density of memories that I'm encoding, or density of patterns that I'm encoding. So for each one of these curves, one can determine the number of encoded patterns by taking the product between alpha S and Vn here. Now, if we look at how the performance varies as a function of the pattern density, the signal pattern density here, we see that basically in all models except for the QAMM model, the performance actually gets worse, as we saw previously in the energy diagrams and the average class bit diagrams. And so really we see here up to about 0.5, which is where we expect sort of the maximum capacity to be in the classical sense for the projection rule. We see that of course the performance actually degrades, except for in this QAMM case. Interestingly, when we go to, let me move this down here for us. When we go to the case of alpha is equal to 1, we see a very interesting behavior here. While the QAMM case seemed to be fairly robust to changes in the density, we see this jump actually where the performance degrades dramatically. Interestingly, when we look at the QCAM case, we see that actually performance begins to increase. Now, is this a sign of a quantum advantage? It's hard to say. Really, what we can say here is that there appears to be some critical clause density where the performance of QCAM, when we're doing class bit classification, it appears that after this critical clause density, the performance improves. And so we're not quite sure why this happens, but this is a very, very interesting result. And so we actually see this occur in many other cases as well, as we'll show you right now. So if we now add in detector inefficiency, and we focus on sort of the best 3 models that we've considered here, what we see is that as we vary the detector efficiency, as I'll show you here, we don't see a very large difference in performance among any of the models here. However, we do see the same behavior as we saw before, that as we increase the pattern density, the QAMM model is very good up until about a pattern density of about 0.5. And then after that, we see a dramatic drop, where after this value, we see that the performance of QCAM with the class bit classification actually increases. And interestingly too, we see that it's very consistent over different values of efficiency. Now, this is perhaps not surprising that we don't see a big effect on detector inefficiency, because this is typically not a large source of error. Actually, detector noise is where we really expect to see differences in performance, and that is indeed the case. So when we go to detector noise here, notice here that I have removed the fits here, and this is mainly just to make it a little bit more clear, the behavior that we're going to see. As we go to detector noise, as we increase the detector noise, we see a much more dramatic effect in the performance of each of the models. However, none so more evident than in the case of the QAMM model, where we see that the performance nearly drops to 0 in many cases, and when it does actually appear to increase, we see that it's along this diagonal where we see basically some of the worst performance that we could expect. Interestingly, though, we see that the QCAM case for class bit classification is fairly robust. So showing again, it's fairly robust, and even in the case when we have a high pattern density. So overall, what we've been able to show is that energy-based classification for QAMM is actually quite good, as long as the number of encoded patterns is relatively small and the detector noise is fairly small. Now, the class bit-based QCAM classification is actually one of the most robust methods, and we see this very interesting behavior after this critical clause density, or I should say critical pattern density, where performance increases. And it's something that we don't quite understand, but it's a very interesting effect that we really do need to try to understand. We also see that performance is actually quite robust to inefficiency and noise, which is not necessarily expected. So that's quite an interesting effect that we've observed here. So in addition to sort of understanding this critical pattern density behavior, We also look to improve the pattern encoding pattern encoding method that we're using here. So right now we're using a one-hot encoding, but this is not the best way to do bit to qubit encoding. And if we use more dense coding methods, then we can reduce the number of qubits, and just by that alone, reduce the inaccuracies of the hardware. Furthermore, we look to use the optimizer, or I should say the control of the annealer to optimize the classification and improve that classification further than what we've already seen. If you have any questions, please feel free to email me about this work. Thank you for listening, and have a nice day.